Okay, we have to accept here. God damn. Where is my mouth?
Let's start.
You can, what? Nothing?
I think we are live now.
Yeah, that's the problem.
Does someone know how to handle the situation?
You know, that's what I had last time we met, like on Zoom. I had the same problem, yeah. And so I spent the whole meeting like this.
Oh, yeah.
Yeah.
But nothing.
Yeah, we tried enter and escape.
Nothing. No key works right now.
Yeah, let's try
Gerald,
putting this up to the top.
Nothing works. No key is working. Okay, we can. Yes.
That's the only solution. Oh, yes.
I think there's just an invisible mouse going on.
What?
Okay,
What?
nice.
Escape worked.
No. We tried. Okay, perfect.
Okay, this was very stressful so far. I hope you have a better rest of the session. Okay, so welcome everyone to the first student presentation of this seminar class. I'm happy to introduce Xavier Sabo, who's a second-year master's student here at Computer Science Department at ETH. He's going to talk about an interesting paper that analyzes various popular and important consumer workloads that are heavily used these days, and see how processing memory can help improve their performance and energy efficiency. So, okay, now you can get started.
Well, thank you, Nika, for this nice introduction. So my name is Xavier Servo. Today I'm going to talk about Google Workloads for consumer devices, mitigating data movement bottlenecks. The first author is Amirali Bourmont, and it was presented at ASPLOS in 2018. So I'm going to start first with a quick introduction and background. But actually, I'm going to start with you answering a question. So tell me, you're all daily users of these devices, but they have one problem. Tell me, do you guys have any idea of what I'm talking about? Like, what is the one thing you want to increase in your phone, for example? Yes? The battery capacity, very well. These devices have a tight energy budget, but that's not the only constraints on these devices. They also have a tight thermal heat budget and a tight circuit area budget. So the question we're going to answer today is actually how to make these Google consumer devices more energy efficient while still complying with these tight budgets. And the first idea is that we're going to take the most popular Google workloads. So these are Chrome, Tensorflow, and the VP9 codec, and we're going to analyze them. So the key observation that the authors make, the first one, is that most of the system energy is actually spent on data movements. So that being the data going up and down the memory hierarchy. The second key observation is that actually only a few simple primitives are responsible for a large chunk of the total energy cost. So the first key contribution of the paper is to take these workloads and analyze the data movements related costs. Then they show opportunities for PIM to alleviate these data movement costs. And actually, they designed the PIM logic and evaluate the efficiency gains. And they see that they can reduce the energy cost by an average of 54.4%, 55.4%, and reduce execution time by an average of 54.2%. So that's kind of like driving a slow car. You know, it's like very efficient. It doesn't consume a lot of fuel, but that's also like driving a very fast car because, you know, execution time is reduced. So it's fast code. So now a bit of, you know, a recap, a refresh on what is processing memory. So first, the philosophy, just simple, processing data closer to memory. And hopefully you're going to get more bandwidth, lower latency, and more energy efficient systems. And the type of PIM, of processing memory architecture that is used in this paper is stacked, is 3D stacked memory. So this is where you have like DRAM layers, and they're all connected to a logic layer via this through silicon vias. And a small aside, we're going to see this multiple times in this presentation. This type of memory is composed of multiple vaults that are isolated. So now before we get into the actual workload analysis, we need to talk a bit about the methodology. First, the machine is a Chromebook, Intel Celeron, 2 gigs of RAM. Then for the performance and traffic analysis, they use hardware performance counters on the SoC. And then for the energy model, they just add the energy of the CPU, the cache, the DRAM, and the off-chip interconnects. So the authors consider two types of processing and memory implementation. The first one is having PIM cores. So these can compute pretty much everything you need. So they're very general purpose. We also want them to be low power, so no fancy instructional level parallelism. And because we're going to see that in the workloads we consider, we have a lot of data parallelism. So we're going to make it in SIMD. The second type of PIM is PIM accelerators. So these are like custom logic for each workload. And again, because of high data parallelism, we're going to make a lot of copies of these accelerators so they can process data at the same time. So now let's finally actually get into the workload analysis. Let's start with Chrome. Why analyze Chrome? Well, it's widely popular, more than 1 billion active monthly active users. But I'm going to ask you now, what makes Chrome feel fast? Like as a user of Chrome, like what do you expect when you actually use Chrome? What makes it feel fast? Do you guys have any idea? Go ahead. Pages load, yeah, page load time, very good. Smooth, yes, exactly, yeah. Okay, good idea. So basically what you said, so page load time, smooth experience, so smooth web page scrolling. And you also want, when you switch to a tab, you want it to be fast as well. So what are we going to do now? We're going to take care of scrolling and tab switching. And actually, if you think about it, the load time reduces by increasing the scrolling and tab switching performance. So let's see what we can do in page scrolling first. I'm going to explain to you what the whole page scrolling pipeline is. So you're on your computer on a bright Sunday afternoon, as you usually do, and you connect to bing.com. Then the server responds to you with HTML and CSS. And then this is where the fun starts. You take this HTML and CSS, this is the loading phase, and you have light parsing of these two documents. Then you make a rendering tree out of them. And then with this rendering tree, you make a layout out of them. This is the layout phase. And basically what it does is calculate the structure and position of each element on the page. After this, you do rasterization and compositing. This is the drawing phase. And rasterization calculates the bitmap of each element, while compositing combines the bitmaps of a layer and actually draw them. Now, if you think about it, those three first things, they're only executed once. Well, these are executed 66 times a second. When you scroll through a web page, you don't care what's executed at the very beginning. So actually, we're only going to consider the two last stages. And we're going to see that in these two stages, there's two subcomponents that are very important for us. These are texture tiling and color bidding. Now, I'm not going to explain exactly now what it is. You're just going to have to bear with me. I'm going to show you some data first. This is not expected. It's fine. Okay, so this is the first graph I want you to see. This is the fraction of total energy across all these different websites for texture tiling and color bidding. As you can see, on the last one, you can see the graph should have been here. It's fine. As you can see, more than 40% of the fraction of the total energy is taken by these two workloads. Here's the second graph I want you to look at. This is, again, the fraction of total energy for texture tiling and color bidding, and it's decomposed by data movement or compute. And as you can see, for texture tiling, more than 85% of the energy that texture tiling costs is spent on data movement. And for color bidding, it's more than 64%. And recall, data movement is evil. So let's see what we can do about this. This is what texture tiling does in the typical CPU implementation. So it reads the bitmap, then it converts the bitmaps to tile texture, it writes them back, and that's pretty much it. So is that component a good fit for PIM? Well, first thing is that, as we said, 85% of the energy consumed is consumed by data movement during texture tiling. The second thing is that actually texture tiling has poor data locality because of the algorithm. And the last point is that the rasterized bitmap is pretty big. So you're reading a big thing in memory. That's bad. Here is the PIM, what PIM does. It basically does exactly this, but it does it in PIM. It converts the bitmap to tile texture directly in PIM. But is it PIM? Is it cost effective to do that? Well, you have to consider first that in texture tiling, it's only very simple primitives like memcopy, bitwise logic, and addition. And in the paper, they see that it will only take 7.1% of total per volt area. So that's good. Now, what can we do about color blidding? Color blidding is this thing where basically to draw an object on a web page, to draw an element, you first start by drawing its components, the very primitive components. So for example, if you have this search bar here, right there, this Bing search bar, beautiful, you have to first consider drawing a line, and then image, and it gives you the whole bitmap. So that's color blidding. Is it a good fit for PIM? Again, 64% of the energy is consumed by data movement during color blidding, and it has poor data locality. And again, as we said, the rasterized bitmap is big. Is it cost effective? Again, simple primitives only, memset, add, multiply for alpha blending, bit shifts. And basically the paper says it would have a small per volt area. So now we have a smooth scrolling experience, and now we want to talk about tab switching. So first, what is tab switching? What's happening there? First, you have to consider that each tab is its own process. It looks like this. So when you switch tab for another, you do a CPU context switch, but you also load the associated page in memory. Page in memory. So the problem you're going to tell me, well, the problem is this. Well, whoops. Yes, the problem is this. The problem, actually, the memory is a big problem. Because today we have increasingly rich web pages, and we need responsive RAM. We really need responsive tabs, so we use DRAM, right? But we all know this person who have like 150 tabs open. Maybe it's you, maybe on your computer have 150 tabs open. Well, when you have too many tabs open, at some point you need to compress it. DRAM cannot accept 1 million tabs. And then when you need it, you just decompress it from DRAM. So now let's see what the energy cost of all this is. So the methodology used in the paper is you open 50 tabs, scroll for 3 seconds, switch to the next. And this is the graph you obtain. So as you can see, for the first 75 seconds or so, nothing happens. This is because you didn't switch to enough tabs to overwhelm the DRAM. So nothing actually went to ZRAM yet. But after this, you basically have this data coming in and out of ZRAM in this weird pattern. So the results is that 19.6 gigabyte of data movement. That's for 50 tabs, 3 seconds each. That's a huge number of a huge memory chunk for such a small methodology, for such a small experiments. And actually 18.1% of system energy is spent on compression and decompression. So what can we do about it? That's what happens in CPU when you want to compress, right? You read the uncompressed page, you compress it, write it to ZRAM. Is that a good fit for PIM? 34.3% of system energy spent on compression and decompression. And also, we have to realize this can be handled in the background. So we're going to see it. So this is bad. We're going to see exactly. Here, you do the same. You compress inside PIM, but actually your CPU can now handle all the tasks for other active pages. But is it cost effective? The algorithm that Chrome uses is called LZO. It has pretty simple primitives. And the paper finds that it will only take 7.1% of total per volt area to do that. So it's pretty cost effective. Very good. So now we're done with Chrome. You have blazing fast tab switching, scrolling, whatever. And now you can go to TensorFlow. What do you want to analyze TensorFlow? Well, so the cool kids are doing. And most seriously, deep learning is becoming increasingly used in mobile applications. Think about what you have to do in Google Photos, for example, when you process images, make beautiful images. So what does it do? Well, in the paper, we only consider convolutional neural networks. So that would only be convolutional operation and matrix multiplication. I mean, after all, mobile is an image first kind of platform. And we're going to see that there's two key operations there. There's packing and quantization. And let's see what each of them do. Let's start with packing. The packing problem, what does packing solve? So when you do a matrix multiplication, what you want to do is that you want to load the matrix or parts of the matrix into each cache such that you minimize the cache miss rate. Is that a good fit for PIM? Takes 33% of total system energy. And during packing, 80% of this energy is consumed only by data movements. Because basically what you're doing is that you're reordering the data in some way or another. Would that be cost effective? Well, as I said, it's a simple memory reordering. And it turns out we can reuse the same logic as in texture tiling. So that would be pretty cost effective. So now we're done with packing. What about quantization? Quantization is basically another one of these optimizations that you do during matrix multiplication or convolutional operation. Basically, you start with a matrix, a float. Then you quantize it, and you end up with a matrix of 8-bit integers. So you're going to tell me, how do you end up with 8-bit integers? You have float, you lose precision, right? Well, that's exactly the point. Basically, you normalize all the elements such that they fit into this 8-bit integer. Then you apply your convolutional layer or your fully connected layer, and you obtain another float matrix. And then you have to, again, requantize it because you're, again, going to apply another layer. So you want this to be an 8-bit integer matrix. So you're going to ask me, why are we doing all this? What is this all about? Well, it turns out that when you do matrix multiplication, it's much faster, or actually these two operations, so convolution and matrix multiplication, it's much faster when you have these quantized matrix. So it's just an optimization when you do these matrix multiplications. Is it a good fit for PIM? 16% of total system energy. And during quantization, 73% of this energy is consumed only by data movements. Now you know the song by now. Is it cost effective? Only simple primitives, shift, add, and multiply in this operation. And we can reuse the same logic as in texture tiling again. So it's pretty cost effective. I mean, as cost effective as texture tiling would be. So now we're done with TensorFlow. We can do all the deep learning we want. And we're going to go back to, a more, an older workload. So that would be video encoding and decoding with the so-called VP9 codec. So what would you want to analyze the video playback and video capture, this codec, right? Well, if you think about it, a lot of these new platforms, YouTube, Netflix, TikTok, Instagram, they're becoming increasingly video first. And a huge portion of the internet, actually, I'll just show you this graph. As you can see, in 2016, it was already the majority of IP traffic was internet video. 2021, that's 67%. And if you extrapolate, you can see it grow up even more, right? So what does the VP9 codec actually do? Well, we're not going to have too much time to get into it, but I'm just going to explain broadly, right? So that is the VP9 decoder. It takes if you want to watch a YouTube video, for example, you're on your phone. Basically, it takes this compressed video stream, it decodes it, puts it on your display. And then, for example, if you use something like Google Hangout and you want to share your screen on your Chromebook, then it just takes the frame from your screen, encodes them, sends them to the internet. Simple as that. And as we said, you're just gonna have to trust me on this one. Most of the system energy is spent on data movements for some of these subcomponents. So it's a pretty good fit for PIM. And the majority of data movements comes from simple primitives. So PIM in this case is likely feasible. So now, before we get into the juicy results, I'm just going to spend some time talking about the system configuration. So they use a full system simulator that's called Gem5. So the main core is quad core. The main the SoC has a quad core. All the PIM cores are just one core, so they're less powerful. They have less cache as well, as you can see. And you have this 3D stacked memory here. And one important thing to note is that the SoC only has access to the channel bandwidth, so the off-chip bandwidth, while the PIM cores actually have access to the internal bandwidth. So that's pretty much what you get when you have like a 3D stacked memory. You have more bandwidth. And the baseline memory is LPDDR3. So that is the graph of the energy for CPU, then PIM core implementation and PIM accelerator implementation for these four workloads that we saw. So we didn't get to see all these algorithms in the video playback and capture. Just gonna have to trust me that these are important, and they're in the video playback and capture in the VP9 codec. And so as we can see, the results are very good. So at best, for PIM cores, at best, you have less than 30% of the initial CPU in terms of energy. And then for the worst, you have 60%, less than 60%. And for the PIM accelerators, it's even better. So 27% of the base energy, and for the worst, 50%. And now what about the runtime, right? The fast car, you want fast car as well, right? So again, we didn't see those, but whatever. And for this PIM core, at best, you have less than 45% of the initial runtime, and at worst, you have less than 85%. And for PIM accelerators, again, even better, less than 40% runtime for the best PIM accelerators, and for the worst, less than 71%. So for conclusion, want to make Google devices energy efficient? We have tight chip area budget and tight thermal budget. Well, you first realize that it's all data movements, 62.7% of the system energy. And then you realize that it's all simple algorithms. Algorithms like primitives like add, multiply, and shift. Then you accelerate the processing in memory. And you reduce energy consumption by 55.4%. And you reduce runtime by 54.2%. And you profit, free up area, make things fast, free up energy budget. So now we're going to get into the actual analysis of the paper. So first for the strength. So the first thing I want to really emphasize here is the breadth of exploration. So we analyze all these, they analyze all these workloads, Chrome, TensorFlow, the VP9 encoder, the decoder. We didn't get to talk about this part, software plus hardware. Basically, the VP9 decoder and codec both have a software implementation and a hardware implementation. So that would be a hardware accelerator inside the SoC. And the paper also analyzes these hardware accelerators. The second thing I want to emphasize in the strength of this paper is, of course, the depth of exploration. So each workload is, first point is each workload is thoroughly analyzed. Second is that each workload not only gets its own PIM feasibility analysis, but also PIM implementation. And then each workload PIM's implementation is thoroughly analyzed as well. And we have basically the first paper to comprehensively profile and analyze popular Google workloads. So now for the weaknesses. First one, I found that there was a bit of a discrepancy between the evaluation methodology and the analysis methodology. Basically, they do not match. So what I mean by that, first point is that in the analysis methodology, so the first part of the paper, when they do the PIM feasibility analysis, the CPU considered as 2 cores. And in the evaluation, the CPU has 4 cores. So when you actually read the paper, you have a bit of a discrepancy where you have in your head the system with 2 cores, and then you do the evaluation with a different system. The second thing is that the analysis is based on HMC memory, and the evaluation is based on the HBM memory. So I'm going to explain. HMC is a hybrid memory cube. So this is the 3D stacked memory we talked about, right? And HBM memory is called high bandwidth memory. And basically, the difference between these two is that I have different bandwidth characteristics. And when they started talking about the analysis of the paper, they talked about HMC. They talked about simulating with HMC. And then for the evaluation, they said, we're going to use a HBM-like memory that has the same architecture as HMC. which I found a bit confusing. Then I think it lacks comparison against a GPU for Chrome, for example, or a neural network accelerators for TensorFlow. So when I have this baseline CPU, right? Like for example, in 2017, there was already a neural network accelerator in Motorola phones. But credit given where credit is due, they do, as I said, they do compare against the VP9 codec hardware implementation. Now, they also lack comparisons against the accelerators on the SoC. So what I mean by that is that basically for Chrome and TensorFlow, they build these PIM accelerators inside the 3D stack memory. What happens when you actually place these accelerators inside the SoC? Just like the VP9 codec accelerator that was inside the SoC. What would happen then? I think it lacks a comparison. And then again, we have in the evaluation, you have this baseline core, and then you have memory, you have HMC memory or 3D stack memory, with each of them having 16 volts, so 16 cores. And basically, what I mean by that is we wanted to decouple the performance from having those in PIM itself from just the simple fact of having more cores. Like how much of that performance improvement is just because we had more cores, and how much is it just because it was inside 3D stack memory? And the last one is that the baseline memory, as I said, uses LPDDR3. So that's it's pretty old, 2012 or 2013 for the first device that used this. That's a 2 gigabytes per second bandwidth. Whereas for the PIM system, they use the off-chip bandwidth of 3D stacked memory. So that's 32 gigabytes per second. So now here are my takeaways. A lot of popular workloads involve very basic operations that can be accelerated with PIM. If you think about it, data movement problems are hard to solve with current methods, but are powerfully solved with PIM. So current architectures are basically designed to try to solve these data movement related costs with all these caches and fancy prefetchers. But here comes PIM, and you have like a new framework, new powerful framework to solve these problems. And this is related to the last point, which is we talked about having improvements of about 2x in terms of energy and in terms of runtime, and they might not seem monumental. But we're talking about the most used and optimized algorithms we're capable of engineering. So in my view, that's actually pretty monumental improvements. The last one is connected also to the previous point, which is, if you think about it, quantization packing, they're not essential to matrix multiplication. They're simply optimizations. But what you can do is with PIM is take these optimizations and optimize them further. And the last point is that the GPU is not necessarily the solution to all graphics problem. Because you could say like, oh, you have this, for example, in the color bidding algorithm, you have this problem of combining all these bitmaps. You could say, oh, just use the GPU. But it turns out if you actually do that, use the GPU for color bidding, you will encounter problems because, for example, for pages, they're like text intensive, like they have a lot of text. It's not very conducive to the GPU architecture because you have to like compute these bitmaps of very small text elements and combine them all together. And basically the authors find that if you actually do that, you have a 25% increase page load time actually. So it doesn't improve necessarily the page load time. So now we can get into the discussion part. I'm gonna start with just a simple discussion question to open this thing. But first, I want you to look at this very famous graph, which is basically the abstraction layer, so-called transformation hierarchy. And the point I want to make is that when you make a change in the logic or the microarchitecture, like we're proposing here, you also have to take into account all the rippling effect that it has on the whole stack, right? So, for example, how to design compilers to deal with these team workloads. Maybe you guys, what do you guys think? Like you have all this existing code that is programmed for CPUs, and now you have a system comes in. There you go.
Yes, so it's like you want to minimize the effort of adopting the new system. So understandably, you want to have some like automatic or semi-automatic mechanism to help you split the workload into like what should be the workload that actually gets offloaded on the end. And then it's like, or for example, automatically generates the boilerplate flow code that you need for actually like performing the upload, because for example, you need to call a bunch of API calls to program the pin unit or stuff like that. And ideally, the compiler should probably automate all of this while only given the input of the program. But like this is likely very hard, so maybe it could be like the programmer could probably do some annotation on the program to say and hint the compiler maybe this is the probable workload that we should upload to the end. I mean, it's basically the same principle we have in other fields. For example, if we have a compiler for a domain-specific accelerator, we also need this type of workload splitting. So like what's special for processing in memory is probably we would need some different set of metrics on what would be suitable for uploading. For example, for domain-specific accelerators, it would probably be if this is very compute heavy or stuff, and now it would be if this is really memory intensive, like if we have some kind of. I mean, I'm blaming all the hands here, but
Yeah, a lot of very good points. Yes, yeah. Well, you talk about the accelerator because you talk about a lot of stuff. The first thing you talked about, I think, is the compiler, right? The compiler design, right? Because you have the metric themselves and you have the compiler, and that's the first one I want to make is that you said like basically automatically identify what needs to be right in
semi-automatic, basically,
yeah,
with the help of the program.
Oh yeah. So that could be like then a programmer's job, like a compiler's job, an OS job, like it could be anything, right?
Yeah, it's both ways are possible. I mean, we could have, for example, if we use the deal, I mean, if you're familiar with OpenACC from NVIDIA, it's like uploads a portion of the program to the GPU, but the code is still just regular C code that you write, and then or portion or whatever. It's like you annotate the program to say that this may be a good fit for uploading up to. I mean, in this same way, we have the same something similar. Okay,
so you have like this C program, and then this
pragmas, we mark this loop, for example, and then this loop can be a good fit. But we have vastly different paradigm in computing. The accelerators are very different. So
yeah,
of course we need something new, but the idea is kind of the same. I guess it's kind
of. But then, what do you think about the fact that maybe you want the system itself to tell you what needs to be exported to by the GPU in this case, right? Because like if you already know, then why do you need a profiler, right? So you want a profiler to tell you like, oh, this piece of code could be great to offload in GPU.
Yeah, that's one way to profile it offline. That's one way of doing it. Or like for example, we have like another interesting approach would be from RowHammer. For example, if we have a program that's automatically being like continuously inspected while it's running, and then you can collect metrics already even when the program is running, and then it may automatically use some suggestions. It's like we have a lot of ways to do this.
Yes, which one? Okay. Anyone else want to contribute on that theme? I think you already said a lot. Yeah, I think we can move on to a second to a couple of papers I wanted to show you about runtime and static analysis. So it's basically on the same theme we're hinting at here. First paper is like a profiler. So exactly what you had in mind. It's a paper PimProf that was released in 2022. And I'm not sure how much you guys want to get into detail here, but basically what these guys do is that before running the program itself, they basically take the program put some instrumentation code here, instrument it first. Then they simulate the code on a CPU versus a PIM system. So it's pure simulation. There's nothing running. It's a layer above. Then they have, from this, they have some runtime statistics. Then they have some cost modeling algorithm that outputs some execution costs, data dependent costs, and context switch costs. And then they have this so-called decision solver, takes all these costs into account, and they perform basically offloading decision, and they tell you what exactly would be the performance gain from this offloading decisions. Second one is from this group, actually, transparent offloading and mapping. So basically in this work, you have a GPU, the center, and you have all these 3D stacked memory. And basically at some points, sometimes you want to offload part of the GPU, part of the code that is running on GPU onto these 3D stacked memory because you want like higher bandwidth, for example. And the problem there is twofold. First, they design a compiler that can basically determine the portions of code that should be offloaded. So that's purely static analysis. And then there's a second problem, because now your code that was in the GPU with a certain memory is now in 3D stacked memory, and you have no guarantee that this code has access to the memory, that the memory is actually loaded onto the 3D stacked memory itself. So that's what they call the mapping problem. And they basically propose a software hardware cooperation mechanism that would also copy the data onto the 3D stacked memory. And the last one on this runtime static analysis theme is PIM enable instruction. So basically here, those two are like, for example, the PIM prof. What do you guys think it touches on in the transformation hierarchy? Like, what does it actually change in the transformation hierarchy? What does it touch in terms of these? Like, surely not electrons, right? This paper is not about like physics. It's higher up. Right, do you guys have any idea? No idea? Yes. Yes. Oh, you want, okay. The programming language. Yeah, that's pretty accurate. So why do you think that? It's a green light. Yeah, that's on, that's on. Oh, okay.
On? Okay. Well, if you're profiling the data, I guess the end goal is to modify the output assembly with whatever your simulation decided, right? So you're changing the output assembly based on your simulation, right? So it kind of lives in the software space.
Yeah, that's very, very accurate. I would say, yeah. I mean, this is kind of like in the gray zone, because it basically analyzes the code itself, but it doesn't change it directly. It just says like, here are the offloading decisions that could be made, and you do what you want with it. But it's not like you actually, it's not like you're a compiler where you actually run the program and it automatically does this, right? It's something you have to actually engage with. And so, for example, for this particular work, the PIM enable instruction, it touches on the ISA, but it also touches on the microarchitecture. So what they propose here is to basically, you keep the initial ISA, okay? You keep all the instructions you already have so that programmers are not mad at you. They still have their little instructions, they're fine. But you add what's called PIM enable instruction into the instruction set. And basically what you do there is that you have two modes. When you have a hint that some instruction could benefit from PIM, basically, you kind of mark them with these special instructions. And then you have basically this PMU, which basically kind of analyzes if the data locality is good. If the data locality is good, what you actually do is that you don't go in PIM. you stay very close to the core, and you compute it here. The data locality is good, so you don't need to go all the way to the HMC, and you return the result. If the locality is not good, then there's a second execution mode where actually the instruction itself goes all the way to these cores instead, and are actually executed inside the HMC. Any other remarks on the static analysis, runtime analysis? Okay, I can go to the discussion about processing memory. So this work, pretty stacked memory. You guys know maybe another type of processing in memory that we saw 2 weeks ago? Talk a bit. That was the Juan Gomez Luna lecture. We talked a bit about other like processing in memory. There was one company that made these. Maybe you know? No one knows? Yeah. Processing near memory. Yeah, that's actually kind of already what we do, right? We have like a logic near the memory. On the memory? Off memory. Yeah, exactly. Yeah, exactly. So yeah, these chips, right? So they have like the logic inside DRAM. And so maybe we could, I should maybe next time wait. Yeah, I don't know. So basically what these guys do, instead of having the logic layer separated from the DRAMs, they have the logic inside the DRAM DIMM. Like it's not inside the DRAM circuits themselves. This picture is a bit misleading. Have to excuse me, but it's on the DRAM DIMM. So like one of these is not a bank, it's actually a logic. So a core. So what do you think we can also use with a hint here? We saw that already 2 weeks ago as well.
Yeah,
Okay, maybe wait.
So again, as you show on the slide, we have processing using memory, where we exploit the analog functionality of the DRAM. And I mean, we have seen things like Ambit, where we can perform relatively simple operations completely within DRAM.
Mm-hmm.
And as you showed, some of the workloads also employ relatively simple like logic or bit shifting. So maybe that could also be used.
Yeah, very good. Yeah, the paper. That's the paper called Ambit, right? That was like these. That's what you're referring to, I think, right? Yeah, the bitwise operations inside DRAM. So that's 2017. But there was actually, you for example, in co-bidding, you have these like a memory copy operations. So maybe you could use a row clone for that particular thing. And then you have this SIEM-DRAM framework that actually is able to do end-to-end B-tier SIEM-D computing DRAM. So now I want to talk about coherence. One of you guys maybe know what coherence is all about? Quick refresher about coherence. Yes.
Well, the memory in the cache has the same value as, for example, in the, officially in the memory, so that we have no two different values.
Mm-hmm. So what's the problem then when you have processing in memory?
If we have processing in memory, we have to write back the processed memory to the cache in order to here.
Yeah. Okay. Yeah. Very good. Yeah. So basically, we have this, right? And basically, that's already something that the paper highlights, is that the off-chip coherence traffic is very expensive. But there was already a solution back then that was by the main first author, that's called a Lazy PIM, 2016. So that's basically cache coherence mechanism for processing in memory that is much more energy efficient than the naive solution that they actually used in these papers, that would be an improvement. So that's basically what it does. There's a lot of stuff here, but basically what you need to know is that this Lazy PIM, what it does is that it executes a lot of these read and writes without even considering coherency. So it does it kind of like, okay, I'm just going to do it and see what happens. And then when they send the result, they send the PIM send the result to the CPU. Then the CPU might say, hey, you can't do that. You have a conflict here. And so it basically says like, okay, restart the kernel and do it again. And then you send it again, and the CPU says, okay, well, this time no conflict. So it's fine. We can go forward. And there's like a more advanced version of this that was, again, same first author that was released 2019 called Conda. And I'm not going to get into the details of it, but there's something called optimistic mode execution. The thinking behind is pretty similar, but I think they have less cost for sending these. Basically, they don't send much coherence traffic at all. Like here, they send coherence traffic. Even if they send it block by block, they do send coherence. But here they send what's called signatures. And basically the CPU is able to decode the signature and commit or execute. And now, maybe you guys can tell me, can you use coherence to do synchronization? We have 5 minutes, so you guys can tell me, can you use coherence to do synchronization? Yes.
I mean, yes, you could, because fundamentally the coherence protocol is implemented on the whatever interconnect as messages. So you could, like by writing to a cache line, you could do the synchronization and express synchronization as a change of the state of cache lines in both parties. I mean, which is actually how people do in usual multi-core processors. But, yeah.
Is that overkill?
Yes, it sounds like retrofitting something that's not originally the purpose onto the system.
Yeah, okay. There's actually a work by this lab. So here, for example, like in this particular work, we need coherence, right? Like there's a lot of these interleaved part of the algorithm, and we need to reuse the result. Like for example, here you have the texture tiles, but you need to reuse them, right? So we need to have a coherence to say like, okay, well, we have the same data everywhere here. But imagine we forget this and we only say like, okay, we'll only need synchronization between the CPU and PIM here. There's nothing else, right? Well, then you can use a paper called Synchron 2021. And basically it's a lightweight way to do synchronization. So, you might use coherence, but here they don't even need coherence. And they use what's called these synchronization engines that look up the synchronization tables. And basically, these are like central units. So these don't talk to each other. They talk to this, which talk to this. And then between each other, they communicate, right? And there's a master synchronization engine. And so there's a last thing. You said something very interesting at the very beginning of the discussion, okay. Which is the metrics you used, right? Like in this particular work, like we do only use energy, right? What other metrics do you guys can like think we can use in general for like characterizing PIM workloads? Yes.
Talk about data throughput, especially with everything being memory transfers, how much data is actually possible to get processed.
So like how much memory, like what exactly, like precisely?
So how much memory, well, I guess it would almost be the same as execution time, but how much memory you can process in a certain amount of time.
So how many like memory operations per like?
Yeah, or how much memory operations, like how much memory can be affected in time.
You have like maybe another metric in mind?
Execution time, but you did discuss that one, I guess.
Yeah, execution time is pretty good. Well, there's basically this very good answer. This paper, Dama, which is basically they did a methodology in benchmark suite for evaluating these PIM systems. And basically here they consider like a lot of different metrics, right? So there's like the so-called MPKI, misses per kill instruction, last to first miss ratio, the arithmetic intensity, right? And then you have the temporal and spatial locality. So these are all like different metrics that you can use. There's not only like energy, right? And I think with that, it concludes my presentation. Thank you for to my mentors, Nika, Mohammed, and Joel. Very nice. You took like a lot of time to they took a lot of time to kind of guide me through all this. So it was very, very, very cool. I had a great experience. So thank you guys for hearing me, and hope you enjoyed. That's it.
I guess while you're switching to the other presentation, thanks for starting the presentations. You were the first person to start, so that's good.
Thank you.
We're going to continue. Your slides were very well done.
Thank you.
I have a couple of comments. Maybe I'll have more comments at the end, but I will correct the record on UpMem. It's not on the DIMM, it's actually each bank has a processor. Maybe you misremembered that, but it's in the DRAM chip. Yeah, each bank has a, sophisticated processor, let's say. Yeah. So it's much more complicated than what we have envisioned, which is good. Well, in some ways, in some other ways, it's not. And the other, I think you actually got into the nitty and gritty of the paper. That's good. You found out some issues. One of the reasons for the discrepancies are because some of these things are done on different systems, analysis and evaluation. So it's very hard to bridge that gap on the systems. I will. Before we move on, maybe I'll mention one more thing. I think the really interesting thing in this paper is the quantification of the data moment overheads on real workloads and real mobile systems. I think you mentioned that, but it's good to emphasize that. And people always thought data moment is important, and there was a lot of analysis of performance, but this paper really analyzed the energy on mobile systems, on workloads that are really popular. So it's good to do that once in a while. And the number is 62% that was mentioned earlier. It actually is lower than what a lot of other workloads actually see today. Yeah. We'll see some of those numbers maybe in this presentation, but yeah. But it was a good presentation and good discussion of general processing and memory issues also. Okay, we can move on, I think.
All right. So next up we have Yi-Jo Han. She's currently in her last year of the electrical engineering bachelor. She's especially interested in hardware accelerators and in memory computing. And she will be presenting another very interesting paper with Google. So with that, please take it away.
Okay, this is working. Okay. Thank you for the fantastic introduction. And I can see that all of you are so excited from the previous presentation. I'll be very thankful if you can pay attention to my presentation as well. And I'll move on to the presentation. First, I'll just jump in right into the executive summary of the paper. The background of this paper is that recently machine learning inference of different models are pushed to the edge devices, and edge computation is emphasized more and more. And the main problem this paper is trying to solve is that the state-of-art edge GPU of Google has three major shortcomings. The shortcomings are, first, it operates significantly below its peak throughput, and it operates significantly below its peak energy efficiency. And also it has a very inefficient memory system. And the key insight the paper gives is that the shortcomings arise from the monolithic design of the edge GPU, and it does not account for the heterogeneity of NN layers that Google has. So the major goal of this paper is to design an edge accelerator that can fully exploit the variation of the layers. So they adopt this key mechanism called Mensa. It is not a cafeteria, but it is a new framework for designing accelerators. And this consists of a collection of smaller hardware that are specialized to specific groups of layers. And to examine the results, they designed this G-Mensa, which is specially designed for the Google Edge NN models. And as a result, they could see that performance and energy was significantly improved, and also inference latency was reduced. So this is the outline of my presentation. I'll first go over the key components of the paper. I'll give you some introduction, and I'll talk about the analysis of Edge TPU and model characteristics. And then I'll describe in more details about Mensa and Mensa G, and I'll go over the evaluation and conclusion. And then I'll give my opinions about the strength and weakness of the paper, and I'll introduce some discussion topics. So let's go to the introduction. So recently, machine learning inference computation is pushed directly to the edge devices. Before edge computing, the raw data was sent to the network from edge devices, and then the machine learning computation was done by the server. But recently, the machine learning computation are done in edge devices, and the results are directly sent to the network. There are several reasons why they do this. So the benefits of edge computation are these four benefits. First, it is much better in perspective of data security and privacy. And also it is much faster, so we can get real-time responses. And it is really important in some applications. And also we can have reduced operation costs. And also we don't have network constraints, so we can compute inference even if we don't have internet connection. And also we don't have to be limited by the network bandwidth. But there are some important constraints of edge computation, because in nature, edge devices are limited both in power budget and also computational resources. So that is why we need specialized accelerator for edge computations. So many companies like NVIDIA, Intel, and Google came up with their own edge devices to solve this problem. And in this paper, we will look deeply into the Google Edge TPU. So these are the edge neural network models that Google Edge TPU has to perform inference of. We have 15 CNNs, 2 LSTMs, 4 transducers, and 3 RCNNs. And they are each mainly used for face detection, language translation, speech recognition, and image captioning. So we have in total 4 different neural network models. And the main challenge that Google Edge TPU is facing is that edge accelerators must inference efficiently across these wide variety of NN models. So I'll move on to the analysis of the current state-of-the-art Edge TPU and the model characterizations. According to this paper, there are 3 major shortcomings of the current Google Edge TPU. The first is that the Google Edge TPU suffers from severe underutilization of processing elements. And second, the energy efficiency of the TPU is far below its theoretical maximum. And also, the memory system of the TPU is inefficient and also ineffective. So I'll go over these shortcomings one by one. First, because it cannot utilize its processing elements, the Edge TPU utilizes only 24% of its peak throughput in average. So the paper shows this figure. The x-axis shows the arithmetic intensity of the models in flop per byte, and the y-axis shows the throughput in teraflops per second. And we can see that the peak throughput is 2 teraflops per second. But we have 2 observations here. The first observation is that CNN and RCNNs achieve only 40% of this peak throughput. And even worse, LSTM and transducers achieve less than 1% of the peak theoretical throughput. Next, the Edge TPU can achieve only 37% of its peak energy efficiency. In this plot, the y-axis is instead energy efficiency, which in teraflop per joule. And we can see that the peak energy efficiency is 1.42 teraflops per joule. So we also have two observations. The CNN RCNN achieves only 50% of the maximum efficiency, and LSTM and transducers achieve only 33% of the maximum efficiency. And third, the HTPU has very inefficient memory system because the on-chip buffer and off-chip memory access account for a significant portion of energy use. If we look at this figure, we can see the variety of NN models, and we can see the normalized energy. So we can see how much energy the TPU is spending on each task. If we look here, we can see that off-chip parameter traffic to DRAM is off-chip parameter traffic to DRAM gets off to 46% of the total energy. And also 31% of the total energy is used in parameter distribution over the on-chip buffers. So we have to figure out what are the causes of these shortcomings. In order to figure out the causes, the paper conducts a layer level study of Google Edge models. So the paper conducts a deep analysis of the models in significant detail at the granularity of individual layers, not the models. So the key insight they have from this analysis that there are significant variation in terms of layer characteristics, not only across the models, but also within the models. So the first insight is that there are significant variations in terms of layer characteristics across the models. When we say layer characteristics, we mean first parameter footprint, second computational complexity, which also means MAC intensity, and data reuse pattern, and inter and intra-cell dependencies. So by comparing LSTM and transducer layers to CNN layers, they found out that LSTM and transducer layer has larger footprints, lower computational complexity, and also they don't have data reuse pattern in LSTM, and they also have special dependencies existing in LSTM layers. So for example, when we look at this plot, we can see the parameter footprint versus the arithmetic intensity for a bunch of layers. So these are the layers from CNN and RCNN, and these are the layers from LSTM and transducers. So we can obviously see that layers from LSTM and transducers have a larger footprint than layers from CNNs. And the second insight is that even within the model, the layer exhibits significant heterogeneity in terms of layer characteristics. So by seeing into the CNN model, they found that parameter footprint and computational complexity varies even inside a single CNN model. And also data reuse pattern also varies according to input and output activation depth and number of kernel at each layer of a CNN. So when we go back to this plot again, let's look at the CNN 13 model. These are the red dots are all layers from CNN 13, but we can see that the floppy ratios varies significantly across even in a single model. So now the paper introduced the root causes of HTPU shortcomings. First, the P underutilization mainly comes from the large fixed P array and single rigid data flow that Google HTPU uses. As we saw from the previous slides, the layer characteristic varies a lot depending on the layers. But the Google HTPU has a large single fixed P array and a very rigid data flow, and it's used the same data flow for every models. So for some layers, the Ps are often left idle, and also the data reuse opportunities are often neglected. So the TPU suffers from underutilization. And also the poor energy efficiency mainly comes from the large over-provisioned on-chip buffer. And also the on-chip buffer uses a large part of the dynamic energy, but it also does not efficiently cache the parameters. So the high cost, the TPU also suffers from the high cost of off-parameter traffic. And also there are memory system issues because the on-chip buffers fails caching for a large portion of the parameters. And so there are like a lot of wasted energy for buffer access. So the key takeaways from these analysis is that the layer characteristics varies a lot, and the Google Edge TPU has a very monolithic design. So that's why the accelerator performance is degraded. So as a result, to achieve high utilization and energy efficiency, key components of an edge accelerator must be customized. The key components here consist of P array size, on-chip buffer, and off-chip memory bandwidth. So now I'll introduce the key mechanism of the paper. So the name is Mensa. Mensa is a new machine learning accelerator designing framework. And as we saw from the slides, previous slides, the problem we're trying to solve is that accelerator performance is degraded due to monolithic design of the accelerator. And also our goal is to build an accelerator that can compute inference efficiently across a large variety of models. So the key mechanism they are using in Mensa is that they're using a collection of smaller hardware that are specialized toward different layer types. So the original Google Edge TPU, they have a bunch of different models, machine learning models, but all layers are executed in a single accelerator. But in Mensa, the layers are first grouped into families according to their characteristics. And then the runtime scheduler of Mensa map the layers onto different accelerators that are catered to each layer's characteristics. So by using multiple heterogeneous accelerators, Mensa can achieve higher energy efficiency and higher performance. And I'll briefly explain the implementation of Mensa runtime scheduler. The goal of this software runtime scheduler is to identify which accelerator each model should run on. The runtime scheduler gets an NN model as an input, and it also gets these two information, the accelerator characteristics and the layer characteristics. And these information are generated only once during the initial setup of the inference. Using this information, the runtime scheduler create a mapping between the layer and the accelerator for each NN layers. It assigns the destination accelerator for each layer, and in the process of assigning, it also accounts for communication overhead using a simple cost algorithm, because if we switch to another accelerator during the inference, we also have to account for the communication costs for moving the data to another accelerator. So this was the overview of the Mensa framework. And in this paper, to evaluate the performance, they create Mensa G, which is a specifically designed Mensa accelerator for Google Edge models. So before they start designing the accelerator, they cluster the layer in two families. So this figure shows the parameter footprint and MAC intensity of each layers of the Google Edge models. So they group these layers into 5 families based on their layer characteristics. So we can see the first 2 families in this slide. The first 2 families are called compute-centric layers. They have lower parameter footprint and high data reuse rate and high MAC intensity. And they consist mainly of CNN layers. And then we see the rest of 3 families. They are called data-centric layers. They have high parameter footprints and low data reuse rate and low MAC intensity. And they mainly consist of LSTM and transducers. So based on their cluster of layer families, they designed 3 accelerators named Pascal, Pavlov, and Jacquard. So I'll explain briefly how the accelerators were designed. First, Pascal is a compute-centric accelerator. It is catered for families 1 and 2, the CNN layers. And it keeps the large P array of the original TPU because the CNN layer usually requires a lot of MAC operations because they have to compute a lot of parallel matrix multiplications. But the activation buffer and parameter buffer was reduced because they have lower parameter footprints. And because the bandwidth requirements of this Pascal accelerator is relatively low, they decided to keep it on the CPU die, which means it's an on-chip accelerator. And there is Pavlov, which is an accelerator for family 3. Family 3 is mainly consists of LSTM layers and data-centric layers. They have a very small P array of 8 by 8 compared to the original P array of 32 by 32 because the data-centric layers have low MAC intensity, so they have less MAC operation to compute. And also the LSTM layers mainly compute matrix to vector multiplication, so they need a lot less processing elements. And the activation buffer was also reduced, and they have no parameter buffer because of the specialized data flow they designed for this accelerator. But I think it will take a lot of time for me to explain all the data flow they designed for this accelerator. And all the details are available in the paper. So if you're interested in this specific data flow, please check out the paper. So the specific data flow designed for Pavlov allows it to stream the data directly from DRAM. So they didn't put a parameter buffer for this. And also its memory bandwidth requirement is 256 gigabytes per second. And it is relatively high compared to Pascal. So they decided to put it inside the memory device, which makes it a near data accelerator. And finally, there is Jacquard, which is catered for families 4 and 5, which are data-centric layers, but they are non-LSTM layers. So they keep a 16 by 16 P array because the families 4 and 5 requires more MAC operation than Pavlov, but less MAC operation than Pascal. It was just decided empirically. And also the activation buffer and the parameter buffer was reduced by the specific data flow they designed for this accelerator. So the details, you can check it in the paper. I'm so sorry. And also its memory bandwidth requirements were quite high. So they decided to make it a near data accelerator, just like Pavlov. So using this Mensa G, they evaluated the performance and energy efficiency of their Mensa framework. So for the energy of analysis, in this figure, we can see the normalized energy of the baseline Google Edge TPU and the baseline Google Edge TPU with high bandwidth off-chip memory and the Mensa framework. And the energy was normalized according to the baseline Google TPU. So from this energy analysis, we can observe 3 characteristics. First, energy spent on parameter traffic was reduced significantly. And if you look at here, the dynamic energy used for on-chip buffer and NOC was also reduced significantly. And the static energy, which is the black bar, was also reduced by 3 times. So the Mensa G improves an average energy efficiency by the factor of 3 compared to the baseline Google Edge TPU. And if we look at the normalized throughput, this here is the average throughput of baseline TPU and baseline TPU with higher bandwidth and Mensa. So Mensa G also improved throughput by a factor of 3 compared to the baseline edge TPU. So in the paper, you can also find out the details about the Mensa runtime scheduler and which cost algorithm it used, and also details about the accelerator's data flows, and the energy comparison with Iris V2, which is a prior state-of-the-art edge accelerator, and also the utilization results and inference latency results of Mensa G. So then I'll move on to the conclusion. So as we saw from the first slide, the background was that machine learning inference of different models are pushed to the edge devices, and we have to execute an efficient and effective inference at the edge devices. And the problem is that the state-of-art edge TPU, which is Google Edge TPU, has 3 major shortcomings. And it is not achieving enough throughput, not enough energy efficiency, and also the memory system of the TPU is neither efficient nor effective. So the key insight the paper provides is that the shortcomings arise from the heterogeneity of NN layers and the monolithic design of the edge TPU. This does not account for the heterogeneity of the layers. And the goal of this paper is that we have to design an edge accelerator that can fully exploit the variation of layers. So the key mechanism the paper suggests is that we should not design accelerator in a monolithic way, but we have to use a heterogeneous multiple smaller hardware that are specialized to the specific characteristic of layer families. So the key result they achieved that the G-Mensa achieves better performance, better energy efficiency, and also lower inference latency. So then I'll move on to the strength and weakness of the paper. First of all, I want to talk about the novelty of this paper. The paper was to conduct an inter and intra-model analysis in layer level granularity. It successfully quantified the significant layer variation in edge NN models, and also it clustered the layers based on the execution characteristics and successfully applied to accelerator designs. And it also proposed a new framework for heterogeneous ML inference acceleration with both on-chip and near data accelerators. And also it provides and evaluates an example of heterogeneous accelerator design for Google Edge NN models. And in the perspective and mechanism, it had the Mensa framework was very well designed, specialized hardware based on the layer clusters, and the execution characteristic of the layer clusters were very carefully considered in the design process. And also the Mensa framework was very practical and applicable. The accelerators in Mensa were designed based on the same architecture with the Google Edge TPU. So it will be easier to integrate into the real hardware system. And also it is very flexible because the accelerator and scheduler can be tailored to different target models. Even if we have to design a new hardware accelerator, the runtime scheduler would be able to incorporate the hardware and decide which layer to map on it without changing the software significantly. So it can be applied to a variety of different models. Yeah. And also in terms of evaluation, it well analyzed the shortcomings of Google Edge TPU and its causes, and the 3 major shortcomings were very clearly shown. And also it successfully identified layer characteristic to design specialized hardware accelerator. And also it created an example design to thoroughly analyze the performance and show that the Mensa framework can be actually applied to existing frameworks. And also in terms of results, it's achieved very good results. It achieved high performance and energy efficiency compared to the baseline Google Edge TPU and also Iris version 2. And then I'll discuss the weakness of the paper. In terms of mechanism, the framework was built based on the 24 existing Google NN models, but the machine learning industry is evolving very quickly, and new models or family of layers that haven't been considered in this paper might emerge in the close future. And also the scheduler algorithm was not the optimal one. So this suboptimal scheduler algorithm could lead to a potential scheduler overhead. It used a very simple cost algorithm that might cause inefficiency, and I'll discuss it later in detail later. Also, there might be an underutilization of hardware resource in this framework, because the Mensa framework does not schedule the layers to be concurrently executed in each accelerators, even though it has multiple accelerators. So the concurrent operation of multiple hardware accelerators was not considered. So if we have a more sophisticated design of the scheduler and consider the concurrent operation, we might achieve a better throughput, better energy efficiency with Mensa framework. And in terms of evaluation, its evaluation was very thorough, but was based only on the 24 Google NN models. And also it was a simulator result, so it was not considering other like realistic hardware constraints. So this was my opinion about the paper, and I'll introduce some discussion topics. So the very main question is that would multi-accelerator framework be the optimal solution of rising heterogeneity of neural network models? This paper suggested the multi-accelerator framework to be the solution of the variation of neural network models, but we might be able to question if this is the best solution for this. Why can't we have a better scheduling in our existing TPU, or increase the memory, or have a better on-chip interconnect, or have a higher memory bandwidth? Because if we use Mensa framework, we might have to build a new accelerator whenever there's a new Edge NN model, and also build a new software runtime scheduler. But if we just make our baseline TPU better, it can be more, the baseline TPU can be more generally used than the Mensa framework. So do you have any opinions about this? Yeah.
Yes, so now I forgot what I had to say, but it's fine. You said basically the question here is that we're using heterogeneous hardware accelerators, right?
Yeah.
And why can't we make a better model? The thing is that I would say maybe that there's not so many new layers that really come. You know, you might update your accelerator every 2 years. I'm not sure, like, how often is the TPU updated, for example, like TPU V1, V2, and V3, like what's the number of years they take to?
Actually, I don't exactly know.
Okay, but like my point would be maybe that because deep learning is not like they're creating like a billion new layers architecture every day, you know, it's not so fast. It's pretty fast, but then maybe you could say, oh, well, every 3 years, we make a new hardware accelerator. When we make it, we analyze what's going on and what's going on with the deep learning research and utilization in the industry, and then we incorporate them. But then my criticism would be to what I just said would be maybe this is a bad idea because your latency of like producing a chip maybe in the meantime, there's a new cool deep learning concept that just came and you're not accelerating
Yeah.
it. And that would be bad.
Yeah, right. That's a good point. Anyone have other opinions? Okay, thank you. And I'll move on to the next discussion topic. The next discussion topic I would like to discuss was that could we think of a better scheduling algorithm for Mensa framework? So before discussing it, I'll introduce how the Mensa scheduling algorithm works in this paper. So the Mensa scheduling algorithm has two phases. In the first phase, it identifies the ideal hardware accelerator for each layer based on the information of accelerator characteristics and the layer characteristics. And in the second phase, it iterates over the layers sequentially and use a very simple cost algorithm. For example, if we have a fixed destination accelerator for layer I, and we're I minus 1, and we're trying to decide an accelerator for layer I. The runtime schedulers compares the communication cost of moving the data to another accelerator to the cost if we used a non-ideal accelerator for the layer. So if the communication cost is higher than the penalties using the I-1 accelerator, we use it. And if the communication cost is lower, we just use the ideal accelerator and move all the data. So basically, it only considers the ideal accelerator and the accelerator that was used just before the layer. So if we use a more complex framework than Mensa G with more than 3 accelerators, this might cause an overhead. So I was thinking that maybe we could brainstorm and think of a better scheduling algorithm, or like just simple ideas, or maybe some ideas about the concurrent execution of layers, because it can also be done by the runtime scheduler.
Unsure what is meant. How can you, like, I would like to first ask you, how do you concurrently execute? Because don't you need the result from the previous layer to execute the next one?
Yeah, but maybe we can, like, if we come up with a very sophisticated scheduler algorithm, we might be able to like execute multiple models at once, or like multiple.
Oh, so like actually having
like
multiple models.
multiple inferences.
So like the models.
executing it.
Oh, okay. So like
Yeah,
either two different models.
Yeah,
that
either two
have-
different models or like 2 different inference data.
from the same model, I guess.
Yeah.
From the same model. Okay. But well, then I don't really understand why would you use? Because I think I mean, what I see on what I can think of is that the algorithm just simply says that it uses the accelerator of the previous layer, just because you know, it's the two. I mean, it has 2 choices. Either it keeps the same accelerator or it moves to another one, right?
Yeah.
So what would be the, like, another? I don't even know what another solution might be there.
Because the current algorithm only takes into account the okay. Oh, you can go first. Please. Yeah.
Hi. Okay. So if I understand correctly, your question is like current algorithm is not optimal, and if we want a more complex scheduling algorithm, then the overhead might be too high. Is that the problem? Because I'm thinking currently the solution is obviously a greedy algorithm, because once you decide the previous layer, the following layer, the decision on the following layer depends on the previous decisions. And for example, if previously, if we can change the result from previous decision, we may reduce the communication cost while have an optimal accelerator for the later layer. So maybe the current problem is that it's not optimal, but it's fast, but it's not optimal, right? So I'm thinking.
Oh yeah.
Yeah, maybe we can have like from several different order and try to see if they have the same result. For example, first we do it sequentially from the first layer to the last layer. And second time we decide some random order or some reverse order. And if we see the decision the same, and if we do not have the same decision, we can use some majority function. And we keep the number of different order a constant. So we have a constant overhead instead of we don't have the scalability issue. Something like this.
Yeah, right. Because like some of the layers must be executed in a non-ideal accelerator, but depends on which part of the sequence the layer the non-ideal accelerator exists. The cost, total communication cost, or the loss of using non-ideal accelerator might be different. So if we come up with a more complex or like more sophisticated scheduling algorithm, we might achieve a better energy efficiency from the new scheduling algorithm. Yeah. Okay.
So the ideal one, is that selected at compile time, or is that something that's detected by the hardware, or is that just something that the software developer says, oh yeah, for this layer, accelerator A is the fastest?
Yeah,
Is that how it works?
yeah, it's decided. It is a software scheduling algorithm, so is it decided on the compilation step?
So I guess one thing that you could do is give like a confidence value. So like how much better would it be to run on this, and this, and then do some kind of minimizing those percentages so you get the least.
Yeah,
in this
yeah, that's a good
direction.
idea.
One option, yeah.
But I kind of see your point about the parallel execution, because I think now some models you have like multiple, like you take the output of a layer and then you apply multiple, you have like the computational graph is not linear, right? It does some crazy stuff, and then it all like combines joins together at some point. So maybe like then the decision is like, okay, well, which of these are we like? Was that your like point maybe? About like parallel execution, like concurrent execution, so-called.
Can you repeat it?
Sorry.
Sorry.
Like how in some models, like sometimes the computational graph disjoints, separate, and then it joins back together. So like then you have like two lines to consider. Like you already done the first portion, and then you have like layers on a chain, like a chain of like computation on one side and another one, and you could do them concurrently. And maybe like that's like hard to schedule then, right?
Yeah, that is
more
also
interesting.
I think that is also possible.
Yeah, it's an interesting,
that's a good point.
interesting take.
Thank you. So any more opinions or ideas? Yeah, thank you for your fantastic ideas. And then I would like to introduce some like main challenge of edge ML acceleration that we might face after this work. First of all, the Moore's law is slowing down. So we want to boost the performance and decrease the latency of our edge ML devices. But using more transistors to boost performance might lead to power and cost rise. And also the neural network workflows are evolving rapidly. So there will be layers with different footprints, data use patterns, and data types. So we might need more programmability and flexibility in our edge accelerators, like in Mensa. And also the combination of hardware accelerator and software platforms would be very important, because the current Google Edge CPU can only run TensorFlow models. So the development of more workflow to build cloud to edge pipelines would be important. And also developing new models appropriate for edge computation might be also a possible choice. So these were the topics that I thought about. So if you want to say or mention something, yeah, feel free to discuss.
When you say developing new models, do you mean like new machine learning models that are easier to compute, or what do you mean exactly?
Yeah, that could be also true. And also we can like work on quantization or quantization aware learning to make it more appropriate for edge computing. Yeah.
Theoretically, the Google Edge TPU could also run PyTorch models. Like what is like it can only run TensorFlow models now, but it's not a theoretical limit, right?
Yeah.
Yeah, you could run it. I mean, in theory, you can like compile, because like it only accepts TensorFlow like models produced by TensorFlow kind of thing.
Yeah.
But then you could easily translate your model from Torch to ONNX and then to TensorFlow, like to the whatever computational graph it uses, right?
Yeah, right.
So is that, yeah, I don't know.
But I think it would be also important to develop like a integrated workflow from like the cloud to the edge devices. So it might can boost the speed of development, or it can like.
What do you mean by integrated workflow from cloud to edge?
Because like you mentioned about like converting PyTorch models, like putting them back into TensorFlow. So, but that also like needs effort and time. So I'm mentioning that.
I think actually
Yeah,
I have another comment to make, because
okay.
that reminds me of something actually, because here you have can only run TensorFlow models. But remember, so basically this paper is about basically saying like, oh, this is a new hardware accelerator we could make. It's great. And it only supports all these like layers, right? But I remember I was trying to do inference on a NVIDIA Jetson. It's like an edge device for robotics.
Yeah.
And I remember that had problem because my Torch model had layers that were not supported by the neural network accelerator on this particular device. So like, then it's like on your point of like getting better workflow and running, being able to run anything. Because here, like I had a problem, like I actually had to solve this inside the model code itself, which was like extremely large. And I had to like remove this layer or, you know, transform somehow the neural network into something that didn't have this limitation. So I do agree with this, like having to have better like workflow, and you have like a lot of these different model architectures now. You have to translate your models into so many different formats. It's pretty, I would say it's pretty bad right now. Like there's probably a lot to be done. We're going back and forth.
No, but on that point of like, oh yeah, everything should be able to compute everything. I guess if you keep going with that idea, you end up not actually having a specific hardware acceleration for one platform, which is, I think, what they were doing. They targeted their main workflows and optimized for those. Whereas if you want something that can compute anything, then you're not going to get that benefit necessarily from custom hardware for a custom acceleration. So I guess it goes both ways, right? Yeah, they're having everything work for everything is nice, but then that's not necessarily possible as much because like this whole Moore's law slowing down, you can't have just everything work faster all the time. You need custom hardware for custom pipelines for if you want to continue accelerating at the speed at which we've been accelerating typically. I think that might be one reason. Also, vendors don't want to like work together, so I don't see why Google would want anything other than TensorFlow to work on their hardware.
Because then you could think about like this is all competition, right? Competition based. Like if TensorFlow is bad and you cannot run enough layers. Because I'm not talking about like being able to accelerate everything. I'm just talking about accelerating deep learning, right? So like the layers are still like in a certain distribution. But here, for example, if TensorFlow is bad, then you just go to PyTorch, and we've seen this transition happen, right? And you could even say like, oh, maybe in the future you have another framework which doesn't have these limitations of being very specialized to these accelerators, and then it would win, and then everyone would use that. Yeah. Maybe you want to comment? Makes sense. Okay, I think we're agreed.
Yeah, because there are like certain applications that edge ML inferences are used. So if we have like integrated workflow for specific applications, like the developing speed would be faster and the cost would be reduced because we don't have to go through like all of the like adjusting efforts. Yeah, so that was what I was trying to talk about. Yeah. Any other opinions? Okay, so this is the end of what I prepared. Thank you so much for listening to my presentation. And I thank so much to my mentors for helping me go through all of this and do all the preparations. Yeah, thank you so much.
So thanks a lot. Mohammed, are you there?
Yes, Mohammed.
So yeah, unfortunately, Onur couldn't stay. He had another conflict. So I guess we can conclude the meeting unless you have something to add.
Yeah, Joel, want to add something on the paper or in the discussion? Hopefully
No.
Joel can hear us.
Joel? Yeah, probably regarding the quiz, Mohammed, you want to remind people?
Yeah, just send email to everyone on Moodle that we just released the 2 quizzes. So please take it now. You have 24 hours to submit the answers. Yeah, all the best to everyone.
Okay.
Thanks for the great presentation today.
Okay, thanks a lot, Mohammed, and bye.